Oh, yay. It's 2 o'clock. We get to work. Okay, so we are little by little working our way through getting caught up with grading. Really, it's true that the delay is caused by our attempts to figure out good ways of giving partial credit. So I ask for your continued patience at the trickle out of the scores. The other thing is that Wade and I are making a grand list of grading anomalies. So when you look through the grades that we have given you, if something is still wrong, so like, for example, some of the multiple choice answers were incorrect on our side, if something is still wrong, send us an email, and it may be the only thing we do is put your name on the list, but we will not submit grades without dealing with the list. So that will be taken care of at some point. The key is to get your name on that list. Yeah?
I talked to the PA about it.
Uh-huh.
She said she'll talk to you about it.
Okay.
Do I still send you that email?
Yeah. Yes, you should still send me the email. If you haven't gotten some validation from somebody saying, okay, we know about this problem, we're handling it, or your name is on the list, you should send us email. Can you believe that I just invited you all to send email about this? I did, because I think we're close. Okay, last time I promised you a recursive definition of a heap, and here it is. You'll notice that for the first time this semester, we've got 2 base cases in our recursive definition. And the reason for that is that the recursive case requires an examination, a comparison with a root of a root with 2 children. So the key of the root is less than the key of either one of those or both of those. Because the recursive case requires that substructure, we have to allow for a single root as a base case, or a single node as a base case. Let me think if that works. Yeah, it's still a little weird because I'm not sure we've covered the case where we have one or the other. We might have to define key, the key of an empty thing, and then we wouldn't need the case. Anyway, the recursive case is the interesting part. It means that each node in the tree, doesn't matter where you put down your finger, I'm putting mine right here, I can be guaranteed that the key of that node is less than the keys and the roots of its 2 children. So I know at any given point that that 8 is going to be less than whatever is here and whatever is here in a heap. Okay? Any question about that? And we're going to exploit that as we talk about this. Any question about it? The implication of that is that every path from the root to a leaf is an increasing path. We'll also need that in our narrative at some point today. I want to remind you, let me ask you some questions about the heap for just a second. Tell me about the structure of this thing. Tell me about the structure of it. What's special about what it looks like? It's complete. Very good. This is a complete tree. We need it to be a complete tree for our particular implementation. We implement the thing using a linear structure of some kind. I will always refer to this structure as an array. If you were actually writing the code for this, you'd probably use a vector. Okay? All right. Furthermore, one last little teeny tiny piece of review from last time. By convention, we lay out the data in the array so that the 0th cell is just empty. We just ignore it. You know, we are not starved for space, and leaving this empty and thereby making this one the root be in cell 1 simplifies our computation, so we take advantage of it. Okay, so the root will always be in cell 1. As a reminder, we can navigate this array structure, just like we do a pointer-based structure, because we have very simple functions that give us the left child and the right child of any index. And we talked about that last time. We'll see it in one spot today, so you don't have to worry about it. All right, I have one more question before we get on with it. What's the height of that structure? If I know it's 3, geez, stupid question. Okay, let me ask that a different way. Suppose I give you a heap and I tell you it has n elements. What is its height? Whisper your answer to the person sitting next to you, or talk it if you like. Say it out loud to the person, somebody sitting close to you. You guys talk to each other. Okay? And now raise your hand if the person sitting next to you said log n. Raise your hand if the person sitting next to you said log n. Yes? Yes? Really? Did you people not talk to each other? Did you talk to each other? What did he say? Did he say log n? Did he say log n? No? You can lie to me if you want to. You can say, oh yeah, all my friends say log n. All right, so the height of this structure is logarithmic in the number of nodes it contains, and we can argue that kind of loosely by saying that at every level of the tree we have half as many nodes as the level below. Okay, so we're kind of like cutting the number of nodes at each level in half. How many times can you cut a bunch of data in half? That's logarithmic, right, Neil? Okay. Okay. Let's see. So I want to take just a half a second to remind you. We are talking about heaps because we were talking about a new implementation for a particular abstract data type. Do you remember what that was? Priority queues. That's right. We were in the midst of talking about implementations for priority queues. This structure right here is our best guess at a good idea. I'll tell you right now that it is simply a different idea, and we'll talk later on about whether it was worth spending all this time on. Okay, if this is an implementation of a priority queue, it must have the following functionality. You must be able to insert into it, that's what we're going to talk about next, and you must be able to remove the minimum from it. And that's it. That's all you need from a priority queue. Okay, so let's talk about insert right here. So I want to do something like insert, well, tell me a value that would be super easy to insert into this structure. 45 would be very easy to insert because I could just put it right there. No, that's not a good idea at all. I'm kidding. Where could I put it? At the end, right? After 11. In fact, if I put 45 right here, that corresponds to drawing this node. I should be drawing it in red ink. That node right there. And you look and you go, oh, look, the path from 45 up the tree is a decreasing path, so that puppy must be a heap, okay? But of course, we don't always want to insert something larger, something that works there. We may want to insert 5. Do you like it? No. So the heap property is destroyed. That is, the ordering from the root to a leaf, or leaf to root, whichever way you want to look at it, is no longer monotonic. Okay, so, that's a problem. So when you learned about sorting algorithms, it's possible, I'm not sure this was all of your experiences, but it's possible that one of the first sorting algorithms that somebody told you about was called bubble sort. And when you learned about bubble sort, it was this act of kind of bubbling up a value into its proper place, okay, in a previously sorted list. probably immediately thereafter, the teacher, whoever it was at the time, said, oh, you'll never use bubble sort. So I'm standing here right now to give you ammunition for defying your teacher from way back when, because our strategy here will be simply to take this value that's out of order and bubble it up the tree, or swap it up the tree into its proper spot. Okay? So what's our algorithm for doing that? It's simply to start here. Look at that one's parent. Where is its parent? Okay, its parent is its index divided by 2. Here, maybe I should fill in these indices. Here, 2, 3, 4, 5, 6, 7. I can't believe you're paying tuition to watch me do this. Okay. So the parent of 5 is going to be at this index divided by 2, which is here. Okay, 13 divided by 2. Oh, thank you. Okay, and we look at this value and we compare. We go, oh, hey, this one is supposed to be less than this one. How about if we swap places? Okay, so there's a simple swap that moves 5 over here and 7 to this spot. On the tree, it looks like this. And then we just continue that algorithm. Where is the parent of 5 now? In cell 3. Good. So we compare 6 and 5. 6 should be lower than 5 in the tree, so we do a swap. Oops. 5 goes here. 6 is moved down. This becomes 6. This becomes 5. And we continue. We take a look at 5's parent, which is in cell 1. 4 is less than 5, so we don't do the swap. 5 has found its home. Okay? Now, I want to argue that this move right here, this move of swapping 6 down and swapping 5 up, was safe. I want to argue that that last little swap that we did and the general notion of swapping a smaller number up is an okay thing to do. What do we know about 20's relationship with its original root? We know that whatever was here is bigger than its root. And we're swapping 5 up. We're swapping something smaller up. So that's transitivity in action, right? We know 6 is greater than 5 and 20 is greater than 6, thus 20 is greater than 5. All right. So it's safe to do that swap. Any question about that? All right, guess what? That was the insert process. That was the insert process. I do have a question for you. I'm going to start a sentence. Well, I'll ask it as a question. The running time of this algorithm is proportional to what characteristic of the tree? The running time of this algorithm is proportional to what characteristic of the tree? The height of the tree, right, very good. Because in the worst case, this thing, whatever we insert, has to walk all the way up the tree, right? Okay, and we already know the height of the tree. Any questions about that at all? All right, so let's look at some code to do this. All right, so this is a function in a heap class. We don't care about what type of thing we're putting into it, except that it must be comparable. The compiler will yell at us if it's not, because, oh, I forgot to say something, but I'll say it in a minute. Because that reheapify function is going to have comparisons in it. And I'll talk about that in a second. Okay, so this code starts by reminding us that we're implementing this thing in an array. And we always have to deal with the issue of the array resizing. Now, I know that you know how to do this already. The algorithm that runs through your mind is not rehashing. It's you double the array and you copy the data. I wanted to illustrate that in this particular situation because it's really cool. So here's a tree, and it's full, right? Like I'm going to say, here's an array, here's the corresponding heap, and it's full, and a new piece of data comes along. Okay, so a new block, a new colored block comes along, okay? There's no room for it. So what we're going to do is double the size of the array and copy in all of this data and then plunk our new data down. Here's the cool thing. This part of the array corresponds to the potential for another new layer on the tree. So what we've done is added this one, and we bought for ourselves all of those free future ads. I just think there's a little bit of magic in the fact that, I mean, of course, all the math works out, but it's so nice that the structure and the math meet in this way. Because what else would you do? If you're building a tree, level order, you'd say, oh, shoot, we're full. Let's have another level. And that's consistent with what we've been doing all along. Okay, any question about that? Okay, so let's take a gander at the rest of our insert. First of all, we're going to increment size, and we're going to plunk the new key into the last spot. Okay, because now we will already have grown the array if necessary. So we're going to plunk the new key into this last spot here, and then we're going to call a function that that will restore the order that we expect from the heap. Now, because this process takes the node and possibly moves it up in the tree, we refer to it as heapify up. Okay? And we're going to start from an index. We're going to heapify up from an index. Is there any question about that? Yeah? It's proportional to the height of the tree. So, is it log? It's a complete tree. This will always be a complete tree. It's broken if it's not a complete tree. So keep that, keep that going, okay? That's going to be important later on. It's important now. It's important to the whole implementation. All right. So let's write heapify up. You know all you need to know to write this. Let's see. So I want to know, this is a continuing condition. The stopping condition is if we're at the root. The continuing condition is if the index is bigger than 1. Very good. So we're going to stop before the root. That is, we're going to continue if we haven't yet hit the root. So if C index is bigger than 1, then if the items at C index, the one we've passed in, that is the value of the key, is bigger than the value of its parent. Wait, how do we get the parent? Wait, what? Where does the parent come from? Yeah, remember, we have this nifty C index over 2 formula that is the parent. So the parent of index is just that index divided by 2. It's integer division, or you can represent it mathematically by floor. Okay? So if our current value is bigger than the value of our parent, current key is bigger than the key of our parent, then we swap. The interface here, I'm leaving kind of up to you. You could just take the items array as given and pass in the array indices and request that swap make the swap, but I'm going to write it out explicitly. So I'm going to write items subparent of C index like this. So we're just going to take the value and switch their positions in the array. Otherwise, and then we're going to heapify up on that parent. Okay, and that's it. Yeah? No, it should be greater than. I should just have the arguments switched. It's a joke. Yes, sorry. Right. It's still the, sorry. So I would love to be able to say that was deliberate, right? Oh, I did that on purpose, but no, it wasn't on purpose. Do you all see why that's a bug and why I'm embarrassed at this moment? Should delight in that. All right, so we want to move it up if it's less than. We want to move it to its position. Okay, any questions about this? Yeah? Uh-huh.
I was wondering, is it because of the way we traverse the tree and stored in the vector? Is the fact that we can do that?
Yep. So all of those things are related. So the question is, why does this whole parent thing work? And how does this it's kind of a question about how does having a parent pointer here differ from a dynamically defined tree? The answer is that the identity between the indices and their positions in the complete tree are tied to the fact that it is a complete tree. So this, the fact that, an element's parent is, in the next level above is the index divided by 2. We can only do that because, two things, this is a complete tree, and we've laid it out in level order, and we started at index 1. It's a slightly different function if you didn't, okay? So I feel like I said a lot of words, and I have no idea if I answered your question. They're all very tightly coupled together, okay? All right, any other questions about this? So I'm going to answer the question one more time again about running time. If you notice, you've got a constant amount of work. All these things are constant amounts of work, followed by a recursive call on something that is one smaller. And you already know that ultimately there will be one of these for every level in the tree. So the running time of this thing is proportional to the height of the tree, which we already argued for complete trees is log n. Okay? Any question? You good? Okay, so that's all I have to say about insert. So this is big O of log n. It is different from what we saw in our linear structures on the very first day we started talking about priority queues. Okay, the other thing we need to be able to do is remove min. Where's the minimum? Yeah, the minimum's going to be at the root, right? Okay, done. My heap fell apart. Can I fix it? Yeah? Oh, you want me to take the minimum child and swap it up? Yeah, great idea. That is an awesome idea. So I'm going to do that. So I'm going to swap 5 up to, I'm going to return 4. Forget about 4. I'm going to take 5 and move it to the root. Do you like it? Oh, now that broke that subtree. And so we're going to take its, well, how do I choose between 9 and 15? The smaller of them, because order is broken if you choose the larger, that's right. And then the smaller of them, yay! Oh, I love that. What a great idea. Do you like it? You should all be doing this. Why? There's a hole. There's a hole in my heap. Uh-oh is right. Okay, so that was a really great idea, but it broke the completeness of the tree. So what we're going to do instead is observe that that 12 was not good, that 5 was not good glue to start with, because choosing that 5 to glue together the two sides resulted in a hole farther down. So what we're going to do, I'm going to erase some stuff. What we're going to do is take a freely available node, something that's super easy to remove from the structure, and use it as the glue. What node would that be? 11 is correct. we're going to take the last value and swap it into this position. So 11 is gone, and 11 now dwells here at the root. But the problem now is one of order. So we're going to fix that by what was originally suggested. It's just that now instead of swapping a hole up, or instead of creating a hole by swapping, we're going to swap 11 down to basically plug the hole that we had before. Okay, so 11 swaps with 5. 11 swaps with 5. I'm doing this all in the tree because it's too messy to do in the array, okay? And then 11 swaps with 9. And then 11 swaps with 'It doesn't, right? It's less than its minimum child. It's already less than its minimum child, so it's certainly less than the other child, so it's at the root of a heap, okay? Any question about that? So that's the whole algorithm. You are going to, save the value that you care about, swap in the last character, and bubble down or heapify down the tree. What's the running time of that already? What's the running time? Again, proportional to the height of the tree. The running time is log n. Good. Okay, so let's write that code. So this is grab the min value. Okay. This one is swap in the last value. That speaks decrement size. Wait, I probably shouldn't write a comment there. Then restore the heap order. All right, any question about that? So let's write the code for restoring that heap order. Let's write the code for restoring that heap order. We're going to start from the root at this point, just like we did here. We started with 11 and asked for, if it's not a leaf, that is, if it has a child, then we do some stuff. How do I check to see if it has a child? How do I check to see if it has a child? So how do I verify that 14 doesn't have a child? Yeah? Yeah, calculate a child index and check to see if it's valid. And what does valid mean? If it's less than or equal to size. Good. Okay, so that's what has a child does. This essentially says, and if it has any child, it will be a left child. It'll be left child of I is less than or equal to size. That's it. Why did I make a helper function for that? Because I probably needed to debug it, right? I'm sure I made a mistake at first. And so I wanted to test out how it was functioning so that I could rely on it and not have to test it in the context of this larger function. Okay, and then I grab the minimum child of C index. Now the reason I use a helper function there is because that actually is a little bit more complex because it has to handle the case where there's only one child, right? So it's either the left child or it's the smallest key of the two children. Because there's that conditional there, and I don't want to clutter up my code with it, I just made a little helper function to do it. And again, probably I had bugs the first time I did it, so I wanted to debug it separately. Okay, so this is going to return the index of the smaller of the one or two children that C index has. Okay, any question about that? Okay, and then I bet I do this time, right? Is that right this time? Did I get it right this time? It's your call. Yeah, it's good? Yeah, because this says, look, if the current item is greater than the minimum one among the pair, then I should swap down with that minimum of the two. Yeah? Wait. Yes. Let's keep going. Swap. And the swap is between these two, so I'm just going to write those again. I'll race you. I don't know what I'm writing. And then after I've done the swap, I'm going to call heapify up on the, heapify down, sorry, on min-child of index, min-child index. Okay? Okay, running time of this again. Big O of log n. Okay, so now things feel a little different because now we have this structure that allows us to do both of the functions in log n time, whereas last time when we had the linear structures, they were constant in one case and linear in the other, or vice versa, depending on the particular implementation we chose. So that's a two-sentence review of last time. You can go look it up. Okay, and we will use this fact going forward when we do analysis and decide what implementation of a priority queue we should use later going forward, okay? All right, so that's all I have to tell you about priority queues implemented as heaps. But I want to take a step back and kind of look at things in perspective. So I said on Monday, probably, that there was this new ADT called a priority queue. And we speculated on some implementations and decided that a heap, which is its own structure, but also its own ADT, would be interesting to use, so that we should at least know about it and talk about its implementation. And then we had a design discussion about a heap. We chose very deliberately whether or not that heap should be implemented using linked memory like we had before or as an array. And we chose the array based on those discussions. And that conversation was pretty rich all the way along. It's the kind of conversation you're likely to have when you're trying to figure out the support systems for a data-centric application. But the layers of abstraction, number one, they go even deeper, right? Like, oh, well, what kind of array? Or, well, I don't know, arrays are contiguous memory. Maybe people have discussions about what they look like on kind of the hardware side. I don't want to do that, okay? But such conversations probably exist. Design conversations exist going the other way as well. Certainly it's true that a priority queue is going to be an option for orchestrating computation of lots of different things. The one that comes to mind immediately is your to-do list. Okay, it's kind of the frivolous one. And I don't know about you, but my to-do list has priority next deadline, right? My to-do list is arranged by whatever the next deadline is. So raise your hand if that's true for you too. Yeah, I have no idea whether that's efficient or not. Maybe in 374 you actually do prove that it is efficient. I think you might actually. We can talk about that later. But anyway, okay, so there's a priority queue there that serves up the next thing you should work on. That's kind of light. there are lots and lots of other applications as well. Process schedulers in the innards of your machine, process schedulers for orchestrating what programs are run, what tasks are accomplished inside your processor. Those are driven by priority queues. And the most appropriate priority to use, that is the way those priority queues are defined, ordered, that's the substance of research, right? If you can come up with a priority queue system that always gives the right priority so as to maximize throughput, you win. Your system is more efficient than anybody else's. One of our researchers recently published work that said, you know, given some constraints on the system, actually a random priority queue isn't a bad thing to do. So random choice is not bad. So just a plain old queue is how I hear that. I don't know. But so that's an area of active research. Furthermore, any kind of event-driven program like video games, they've got a priority queue set up in place. In fact, the priority is usually the next event that should happen. But that varies depending on the gameplay. Probably most important to us as this class, for this class, is that the algorithms we use to navigate other structures are going to depend on a priority queue. So for example, we're going to look at an algorithm called shortest path, and one of the key structures supporting that algorithm is going to tell us the next best path to explore. That phrase, best path, next best path, that's just handed to us via a priority queue. Okay, so there are applications of these things all over the place. You'll see them. I guarantee you at some point you'll be in a study group with friends and you'll go, oh, I know, we should just use a priority queue. So I'll just write this here because it's good. Okay, but we're really not done talking about heaps. Here's an array of things. It lives in data like this. I'll tell you that right now. Is it a heap? Is it? So look at a counterexample. Look at the counterexample. Figure out how to prove to me that it's not a heap. I think all you got to do is put your finger on that. It's broken all over the place. There is no sense in which this thing is a heap, right? Like there's very little order in any of the nodes. To prove that it's not a heap, you just have to give a counterexample, and I'll point to the one that says, oh, look, A is beneath L. That's broken. Okay, now, this thing is not a heap. It's just an array of data, and my goal is to turn it into a heap. Okay, because maybe these are all my keys and I need to, you know, kind of get them ready to use as a priority queue. All right, so how am I going to do that? What am I going to do? This is my data. It's not a heap. I need to make it into a heap. Who said that? Who am I talking to? Yes, really good idea. He said, sort it. Okay, so that's a great idea. So the first possibility is we could sort the array. What algorithm do you want to use to sort it? Yeah, let's use merge sort, and that is big O of n log n, and it requires, we probably would want to have a buffer to help us do it, but it doesn't matter very much, okay? So we could just sort this data. We could call the standard sort function, and it will do the merge sort for us. It might use quick sort, but in this case, quick sort is actually likely to have pretty bad behavior because lots of times when you're building a heap, you have kind of quasi-sorted data anyway. And the time that that quick sort works badly is when your data is pretty much already sorted. So So we're going to use merge sort here. It doesn't really matter. N log n. Great idea. Oh, what's the proof that sorting the data actually results in a heap? We need the characteristic to be that any path from root to leaf is an increasing path. You probably proved in your calculus class when you talked about sequences that any increasing subsequence of a monotonic sequence is itself monotonic. Okay, so any increasing sequence, so of the indices, when the indices are increasing, that subsequence, whichever one it is, will be increasing if the original data is sorted. And that's all we need here, that argument, because that argues that every path from root to leaf is increasing. Okay, but there's another way we could do this. There's another way we could do this. You have the power. Yeah? Oh, look for the counterexamples. So looking for the counterexamples and swapping them up will create new issues, I believe, because you might swap something up and then create something that needs to be swapped down simultaneously, right? Like you can't control whether an additional swap will be necessary, right? Yeah, maybe that's just bubble sort. So later I can show you a case where that will get you into this mess, unless you can define exactly where that has to happen. Okay, so yeah, good, really good. Okay, so look. If right here before, so we're gonna do a process. If I just read this cell, I go, oh, look, an empty heap, right? How can we insert into an empty heap? Well, I know, let's do insert of B, right? Put B into the first available spot, call heapify up, and then we're good, right? So now we know we've got a heap containing B. And so then we can insert U, right? Call heapify up. Does anything happen? No, it's fine. Then we insert I, everything's fine. Then we insert L, what happens? We call heapify up as part of the insert and it gets inserted. Perfectly fine. Well, that is a reasonable strategy. I'm going to call it repeated insert. It basically consists of a for loop set up over the structure, calling heapify up on every piece, okay? Repeated insert is basically heapify up over the whole array, okay? So that, what's your instinct about the running time for that? Yeah. It's also in log n. Okay? There's a third strategy. I think you can come up with it, but I'm going to help you. Okay? There are some nodes for this tree and for any other, for this complete tree and for any other one that can already be considered to be heaps. Which ones are they? Turn to your partner and tell them which ones. You can tell them what color they are even in this context. Turn to somebody sitting next to you. Okay, raise your hand if the person sitting next to you said the leaves. Okay, good. You can make the person sitting next to you feel really good by lying to me. Okay, all right, so these guys are already the roots of heaps, right? Okay, so I'm gonna just go with that for a minute. If my data were just W, I go, oh, you're a heap, yay. Oh, you're a heap, N. Oh, you're a heap, P's a heap, A's a heap, the root of a heap. How's E? It's also the root of a heap, but we're kind of lucky, right? How about H? It's also the root of a heap, but we're kind of lucky. How about D? Oh, it is. Oh, I forgot. Okay. How about L? Uh-oh. Okay, our luck has failed us, but we know how to fix things. If we have a tree where we know this is a heap and we know this is a heap and we've got a key, we can restore the heap how? Heapify down, that's right. Switch L with its smallest child in this context. So A will come up and L will come down, and now this is a heap, yay. Okay? Now, let's see, we got to here. So everything up to, you can pretend the swapping happened, everything up to here is a heap. Now we look at I. Is I a heap? Happens not to be, right? And so, though, we can make this into a heap if we heapify down, right? Swap E up and I down, okay? Furthermore, same story here, and then finally at the root. So think about what we did here. We said, okay, you guys are all heaps for sure, because you're leaves. Now, heapify down. Heapify down, heapify down, heapify down, heapify down, etc. And at the end, you make a heap, okay? So I'm going to call this heapify down from the end. What's your instinct tell you is the running time? The heck? Really? Okay. Don't you wish? Yeah, okay. So this is the winner, winner, chicken dinner, right? So what's going on here? Of course, we're going to prove this next time. But let me explain what's going on a little bit. Whoa, I said the words next time, you guys are out? I have 2 minutes. Bye. I don't know how to feel about that. And now we only have 1 minute and 30 seconds. Okay, so here's what's going on. In this strategy, so really it's these two that feel like they're the same. I mean, I'm looking at the code. They feel like they're the same, right? It's a for loop and a thing that might go all the way. But here's the thing. In this case, there are a lot of things. All of the leaves might travel all the way up the structure, right? Whereas in this case, the only thing that is going to incur the total cost from top to bottom, the only thing that's going to do that is the root. And in fact, most of the data, all this red, all those leaves, or at least half the data, there's no work done at all. When you carefully add up the work, you end up showing, it's not unlike the whole argument for doubling the array and copying the data, you end up showing that the total amount of work that you do is big O of n in this case, and big O of n log n in this case. And that's all I have. And you guys should go find those guys and tell them I gave you all the answers. Look it. We got to the last slide.
So, in here,
Mm-hmm.